Today, to start number 3 that deals with instance-based learning and feature selection. So what we are going to study in this unit? In this unit, we are going to discuss two algorithms under instance-based learning, and these two algorithms are known as k-nearest neighbor algorithm and distance weighted nearest neighbor algorithm. Then we'll see one problem with the learning algorithms, and that problem is known as curse of dimensionality. So this curse of dimensionality actually deals with the huge number of features describing the instances. So we are going to look at what does this mean, and then we'll see the solution to deal with or to cope up with this curse of dimensionality. So under that, we are going to look at few algorithms under feature selection and feature extraction methods. Under feature selection, we are going to look at filter methods and wrapper methods, whereas under feature extraction methods, we are going to look at one algorithm, and that is known as principal component analysis, PCA. And obviously, while discussing all those details, we are going to look at few applications or case studies. So this is the agenda for this unit number 3. So let's begin with the concept of instance-based learning. So what we mean by instance-based learning, and what is the difference in the learning algorithms? Those are known as instance-based learning, and the learning algorithms, those we have studied so far. Instance-based learning is one way of solving the tasks of approximating discrete or real functions. So this is a kind of learning where we are trying to approximate discrete or real valued target functions. But in contrast with the earlier learning algorithms, those we have studied so far, these algorithms try to explicitly describe the target functions based on the training examples provided. I'll repeat, in the earlier discussion, whatever learning algorithms, those we have studied so far, these algorithms were explicitly describing the target functions, right, by making use of the training data set. But here in instance-based learning, we are not going to construct a general or explicit description of the target function, but instead the training examples are simply being stored, right? And whenever the test sample is presented for classification or for prediction, then and then only these training examples are being used. So that is the main difference in the instance-based learning and the learning algorithms, those we have studied so far. In, say for example, if we consider the learning algorithms, say logistic regression or linear regression, then in these kinds of algorithms, we use training data set, and based on that training data set, we first prepare the model, and whenever the new test sample is being presented, by making use of that model, we were able to predict the or the unknown that was presented. That is how we have learned the learning algorithm so far. But in instance-based learning, what happens is there is no general explicit target function that is being defined based on training examples. Instead, the training examples are simply stored, and whenever the test sample is being presented to the system, all those training examples are being used for computations. And that is why these kinds of algorithms are also known as lazy learning methods. Lazy learning methods. So let us compare lazy learning and eager learning. So the earlier algorithms, those we have studied, are eager learning algorithms, whereas the instance-based learning algorithms are lazy learning algorithms. So what are lazy learning algorithms and what are eager learning algorithms? In lazy learning algorithms, the learning does not occur until the test sample is presented, and that is why it is called as lazy. So the algorithm is lazy. That means it is not at all learning whenever the training examples are presented. Instead, the training examples are typically been stored, right? And whenever the test sample comes in, then only the learning algorithm starts computation. In contrast, eager learning algorithm carries out learning without knowing the test example. So in case of eager learning algorithms, what happens is once the training data set is presented, at that time the model is being created, right? So model has been generated, meaning the hypothesis is designed or the hypothesis is defined while training, and that hypothesis is then being used for testing, right? So the computations at testing are very less in number, right? So in eager learning, learning without knowing the test example. Only thing is they should know the training data set, right? And after learning, it is possible in eager learning that after learning, the training examples are totally discarded, because after learning, there is no use of these training examples, right? Because the model is being created, and for further testing, only the model that has been created is used. So no need of training examples once the algorithm has learned, right? So this is what the difference in lazy learning and eager learning. I hope you must have understood. If you have any doubts, please let me know. The concept of lazy learning and eager learning.
Yes, ma'am.
Fine. So let's begin with the algorithms, those we are going to study in our discussions. So under instance-based learning algorithms, we are going to look at the nearest neighbor algorithm and distance-weighted nearest neighbor algorithm. So let's begin with the most popular nearest neighbor algorithm, and that is known as K nearest neighbor algorithm. K nearest neighbor algorithm, or popularly it is being known as KNN algorithm. K nearest neighbor. So this K nearest neighbor algorithm relies on the general assumption, and that assumption is things that look alike must be alike. Things that look alike must be alike. What does this mean? If we have been provided with different objects, say 1, 2, 3, 4, 5, 6, and so on, right? So what this algorithm assumes is, if this is the object, if I am presenting a new object, suppose I am presenting a new object, okay, and this object looks like this, then if I am presenting this object, then the class of this object will be assigned similar to that of the class which is similar in appearance of this. So this is the red circle. So obviously we may say that class of this, suppose red circle is the class 1 and the green rectangle is class 2. So if I am presenting this object, test object, then what it assumes? It assumes that who is similar looking object. So obviously this red circle. So this test sample will be assigned the red class instead of this green class. So this sample will be assigned circle class instead of rectangle class. So this is the assumption that is being used for k-nearest neighbor learning algorithm. So things those look alike must be alike. So obviously if we want to implement this algorithm, we need to mathematically think of this expression. So what we need to do is we need to find out the similarity between the objects. Right? We want to find out the similarity between the objects. Now, let us go through this k-nearest neighbor learning algorithm. So, as I stated, this KNN or k-nearest neighbor learning algorithm is the most basic form of instance-based learning method. Most basic form of the instance-based learning algorithm. The algorithm does is the instances. It remembers all the instances. Those are being provided as training examples. Right? So whenever we present a training data set, all those training examples are being stored. By instance-based learning, instance-based learning is actually the lazy learning method, meaning we are not going to prepare any kind of a model at the time of training. In other learning algorithms, those we have learned so far, we have created earlier the model based on the training examples. Say for example, if we are talking about the regression, linear regression, then based on the training data set, we used to prepare the model like y equal to mx plus c. Right? So this is the straight line form. So we try to find out a model like this. But in case of instance-based learning, the training examples are only remembered or stored in memory. These training examples are not being manipulated, or we are not explicitly preparing any kind of hypothesis. Yes.
Hello.
I was actually explaining you once again what is the difference in the algorithms, those we have studied earlier, and the instance-based learning algorithm methods. In the eager learning or in the algorithms, those we have studied so far, what we did, we used to prepare a model initially based on training examples, and further for prediction that model is being used to predict the test sample. Instead, in instance-based learning, what we do is, it is a kind of lazy learning, meaning whatever is the training set, that training set is simply remembered or stored, and that is not being manipulated. We are not at all going to build any kind of model based on training examples. Instead, what we are going to do in instance-based learning is, whenever we present a test sample, at that instance only, all the training examples are being considered and some computation is being performed. And based on that computation, at the time of classification or at the time of prediction only, the training examples are being used. right? So that is the difference in lazy learning and eager learning. So nearest neighbor algorithms are the instance-based learning algorithms. Those come under prediction, right? So whatever are the instances are in our training data set, instances are the points in dimensional space. What does this mean? This means that every instance in the training example is described with a feature vector with n number of features. Obviously, then I am having two features and the instances are sprayed like this in this space, right? But just imagine, it is not possible to draw n-dimensional space. So just visualize that similar to x1 and x2, we are having n number of features. So obviously, we will be having n dimensions. And in this n-dimensional space, these points are placed. Right? So this is how we are making use of all those instances. And whenever the test sample comes in, at that time only all those instances spread across n-dimensional space are being used for computation. Let us see how. See here one example. Suppose we are having these data points. This is a two-dimensional space, just for simplicity. So in this two-dimensional space, we are having these objects. Those are placed somewhere in this 2D space. So these objects, green color objects, belong to one class and these red objects belong to another class. Now, whenever a new sample is presented, suppose this is my new sample X. Whenever this new sample is presented to this space or this problem, then what happens is we try to find out its closest training example. Its closest training example. What we mean by that? All these are the training examples and this hollow circle is my test sample. Right? So this is test sample. And these are the training examples. So whenever this test sample is being presented, what happens is we try to find out its closest training example. Let us assume that this is the closest training example, xi, yi. What is xi? This is the ith training sample and associated label for this training sample is yi. Right? So, if we consider this as the test sample and if we try to find out which is the closest sample to this particular test sample, then obviously we will be selecting this red circle, this red object as the closest training example. Right? So, obviously what we are going to do is, if this is the closest neighbor for this test sample, then whatever is the class label associated with this closest training example, that is being assigned to this test sample. And this test sample will be predicted with class yi, which is the class of the closest training example. So, prediction of the class of this test sample would be this yi. And what is this yi? Yi is the class of the closest training example. Have you understood the concept? Yes?
Ma'am,
Yes.
If yi is a class, then what is xi? Means what do you mean by class here?
Class is the discrete class label.
Okay,
Class
okay.
1, class 2. We have learned all those things. This is not new. The examples in our training set, we used to describe those examples in the form of xi, yi. What is this xi? Xi is a feature vector. This feature vector is actually describing the instance or the sample I. So xi is a feature vector that describes this instance I, and associated with this xi we are having known class label yi. It may be any discrete value. For classification problem, yi is the discrete value. So class 1, class 2, class 0, 1, whatever it may be, positive, negative. Here we may say red, green, whatever may be the class. So class label is associated with the training example. So whenever the test sample is being presented, the closest training example is found out, and whatever is the label associated with that training example, that label is being associated with the test sample. So test sample is being predicted with this class yi. So in this example, if this training example is closest to the test sample, the class of this may be red. So yi may be the class label, say red. Then this instance will be assigned that class label, red. Class label may be anything depending on the problem statement.
No, ma'am.
Fine. So let us go into the details of this algorithm. So obviously in this supervised learning we are having training phase and we are having test phase. So or the prediction phase. So in training phase, as I stated, we are not going to manipulate anything, but simply we are going to store the, that's all. Training phase consists of storing the training examples. And what we are going to do in test phase or in prediction phase. Suppose a test sample or the query instance is presented, which is denoted here as X superscript Q. So XQ is actually the test example or the query instance that is being presented to the system. Then what it does is, it finds, we are talking about in general k nearest neighbor algorithm. So k may have some value associated. K may be 1, k may be 3, 5 and so on. Right? So whatever may be the value of k, depending on that value of k, we are going to find out k training examples that are closest to this query instance XQ. I'll repeat. If, say for example, my value of k is 3, then what I'm going to do, this should be 2. What I'm going to do, I'm going to pick 3 training examples. Those are closest to XQ. If I'm having k value equal to 5, then what I'm going to do, I'm going to find out 5 training examples. Those are closest to XQ. XQ is my test sample. If k is 1, then I'll be finding out only one training example that is closest to XQ. So depending on this value of k, we are going to find out k training examples. Those are closest to XQ. Right? Now, classification, if the problem is classification problem, then what we are going to do is, we are going to predict the most frequent class from yi's. Those we have picked up out of this K. And if it is the regression problem, then what we are going to do is we are going to predict the mean or average of yi is. So what does this mean? Suppose, let us assume that we are having K equal to 3, right? And this xq is being presented. So suppose this is, let us assume that we are having few samples. Suppose we are having few samples, those belong to two different classes. Right? So we are having circle class and we are having this another class depicted here as the cross. Now, if the test sample is being presented, if the test sample is being presented, suppose this is my test sample, this black dot is my test sample. If this is being presented, then what will happen? If my K value is 3, if my K value is 3, what the algorithm will do? It will find out 3 samples, those are most closest. 3 samples which are closest to this XQ. So this is my test sample XQ, and this algorithm will try to find out 3 samples, those are closest to this sample. So let us assume that suppose the first closest sample is this, right? The second closest sample is this, and the third closest sample is this. Let us assume that these 3 are the closest samples to this XQ. Okay? Now, as this is the classification problem, that means the output expected is class label, right? Discrete value. If this is the classification problem, then what my algorithm will do? My algorithm will predict most frequent class from yi's. What does this mean? See, if this is the first sample that is closest, suppose this is x1, y1, right? This is the second sample that is closest to the test sample. Suppose this is x2, y2. And this is the third sample that is closest. So this is denoted here as x3, y3. So out of these 3, what is the most frequent class of these yi's? This y1, y2 and y3. For these 3 samples, there are 3 classes. Y1 represents one class and also. So which is the most frequent class from these 3 yi's in this example? Most frequent. So what is the majority? Yes? Out of these 3, what is the majority class? Which is the class that occurs maximum times? Yes. Out of these 3, this cross appears 2 times and this circle class appears 1 time, only once. So majority or the most frequent class is this cross because it appears twice. So this cross appears twice and this circle appears only once. So 2 is greater than 1. So majority, most frequent class that appears is this cross. and that is why the label associated with this XQ would be this cross. So we are going to predict that this test example XQ belongs to this particular class. Are you getting me? Yes or no?
Yes, ma'am.
Fine. So this was related to classification. If the problem is regression problem, what does this mean, regression problem? Once again, the procedure remains the same. Only difference is here this y1, y2 and y3 is not a discrete label, but it is some value. Right? Suppose this y1 is the value, say 10. This y2 is suppose 12 and this y3 is suppose 13. Let us assume that these labels are not the discrete labels, but now the predicted values are the continuous values because the problem is regression problem. In this case, what will happen? Whichever are these closest examples, right? And these yi are the continuous values. So mean or average of these values is being computed, and whatever is the average, that average is predicted as YQ. XQ is my test sample. So we want to predict this YQ for this XQ. So how this YQ is being predicted in case of regression? Whatever are the continuous values associated with the closest training examples, the mean or average of these values is being computed, and that is being predicted as YQ. Got it? So this is how regression works. Is there any doubt? Yes? Is there any doubt? May I proceed? May I proceed?
Ma'am, means in classification it predicts the which it class belongs to, and in regression it predicts the actual values.
Yes.
Like this.
Yes. Meaning is the same. We have seen earlier what is classification and what is regression. In classification, we predict the class level. In regression, we predict the continuous value.
Okay, ma'am. Yes,
right? So if the problem is classification, the most frequent class from the closest sample is being assigned to the test sample. If it is a regression problem, then the average of yi is found out, and that is being predicted, right, as the regression value for the test sample. That's all. Right? So now we are trying to say here that we are finding out the closest training examples. But how to find out this closest training example? Why I am saying that this is closest? Why I am saying that this is closest? Or why I am saying that this is the closest? Right? Obviously, we should compute something. We should find out the distance between the test sample and every sample in my training data set. And whichever are the distances, those are minimum, those are closest, obviously. So we are having here some way to find out these closest neighbors. So Suppose we are having the instance xi with n number of features. So xi is described as I so on up to xni. What does this mean? This xni denotes the value of the nth feature of instance I. Right? So for instance xi, we are having this feature vector. Similarly, having another instance, say xj. If I am having another instance, say xj, then this instance xj is denoted as x1j, x2j up to xnj. So this is first feature in this jet instance, second feature of jet instance, and so on. Right? So we are having now two instances xi and xj. Right? Wherein these two instances are described with n number of features. Then what we are going to do is we are going to find out the distance between these two instances xi and xj, and we are making use of Euclidean distance. Right? So we are going to compute the Euclidean distance between two instances xi and xj. So we are making use of this simple formula to compute the Euclidean distance. So what this formula is? See here, we are having Euclidean distance between 2 points defined as square root of summation over r equal to 1 to n xri minus xrj square. What does this mean? How many features we have? We are having n number of features, right? So my xi is described with n features and my xj is also described with n features. So what I'm going to do is I'm going to pick rth feature of ith instance and rth feature of jth instance. What does this mean? R varies from 1 to n. So if this is my feature vector for xi and this is the feature vector for xj, then what we are going to do is we are going to find out the difference between x1i and x1j, x2i and x2j, xni and xnj. Right? So this is the difference in the respective features of two instances I and j. Right? So we are having squared difference of that. All those squared difference. Finding out the distance between 2 points in this space. So if these are 2 points in this space, one is denoted as xi and another is denoted as xj. Then what we are going to do is we are going to compute this distance between these 2 points, and this distance is Euclidean distance if we apply this formula. So what this formula says, xi is denoted with this feature vector, xj is denoted with this feature vector, and simply we are going to compute the difference between the respective features from ith instance and jth instance. We are having the squared term of this difference. Then we'll be summing up all those terms for n features, and then we are going to find out the square root. So this is how we are going to compute the Euclidean distance between 2 points. Right? So this distance is being computed for every pair with respect to Say for example, let me give you once again the example. Suppose this is my space, and as I stated, we are having the samples, those belong to two classes. This is one class and this is other class. Okay, and let us assume that we are having this test sample. Okay, so what we are going to do is we are going to find out the Euclidean distance between this test sample with every training sample. Are you getting me? We are going to find out the Euclidean distance between this test sample and every training sample. Right? So, we are going to find out this distance. We are going to find out this distance. We are going to find out this distance, every distance. So, in distance between each pair of test sample and training sample. So, we are going to find out all those Euclidean distances. We are going to arrange those distances in ascending order. In ascending order. What does this mean? The first distance will be the minimum, then second minimum, and so on. Right? So, whichever is the minimum distance, that is the closest match. Whichever is the minimum distance, that is the closest match. Okay, so if my k value is 3, then what I'll do? I will pick these first 3 samples which are closest. Right? If my k value is 5, then what I'll do? I will pick first 5 samples. Those are closest. Right? And based on that group of samples, those we have found out as the closest samples. If the problem is classification, we are going to find out the most frequent class. If the problem is regression, we are going to predict the average of yi is as yq. Are you getting me? Yes? Is there any doubt? Yes? Is there any doubt? Have you understood how to compute Euclidean distance between 2 points? Yes or no? How to compute Euclidean distance between 2 points? Yes?
Yes, ma'am.
So, what next we are going to do once we find out the Euclidean distance between the test sample and every other sample from the training data set? We are having obviously all those distances available. Correct? So, we are going to arrange those distances in ascending order, and depending on the value of k, we are going to pick the top k samples. Those are most closest. If the distance is small, that means these samples are closest. Right? So, we are going to pick k number of samples. Those are most closest based on this Euclidean distance. And once we have found out k samples, those are most closest to the query instance based on our criteria of classification or regression to predict the value yq. Is there any doubt? Yes?
No, ma'am.
Fine. So I hope you must have understood what is k nearest neighbor algorithm. Okay. In the next class, we are going to formally define one expression for finding out this majority class, right, or the average. Okay. And then in the next class also we are going to look at one example. And one more issue that we are going to deal with k nearest neighbor is how to find out this value of k. Right? Just I mentioned that k may be 1, k may be 3, 5 or anything. So how to determine this value of k? Right? So in the next class we are going to discuss all those points. Right? So let's stop today. Thank you.